This module will cover description of standard for serial interface and UART which implements it. In telecommunications, RS-232C is a standard for serial communication of data. It defines the signals connecting between a DTE data terminal equipment such as a computer terminal and a DCE data circuit terminating equipment, originally defined as data communication equipment such as a modem. The RS-232 standard is commonly used in computer serial ports for asynchronous serial interface. The standard defines the electrical characteristics and timing of various signals used in serial interface, the meaning of signals and the physical size and pinout of connectors. The current version of the standard is TIA 232F, called Interface between data terminal equipment and data circuit terminating equipment employing serial binary data interchange, issued in 1997. An RS-232 serial port was once a standard feature of a personal computer. It was popularly used for connections to modems, printers, mice, data storage in cassette tapes, uninterruptible power supplies, and other peripheral devices. However, RS-232 is hampered by low transmission speed, large voltage swing, and large standard connectors unsuitable for laptops and tablets. In modern personal computers, USB has replaced RS-232 from most of its peripheral interface roles. Many computers do not come equipped with RS-232 ports and must use either an external USB to RS-232 converter or an internal expansion card with one or more serial ports to connect to RS-232 peripherals. Nevertheless, RS-232 devices are still used, especially in industrial machines, networking equipment, and scientific instruments. In RS-232, user data is sent as a time series of bits. Both synchronous and asynchronous transmissions are supported by the standard. In addition to the data circuits, the standard defines a number of control circuits used to manage the connection between the DTE and DCE. Each data or control circuit only operates in one direction, that is, signaling from DTE to attach DCE or the reverse. Since transmit data and receive data are separate circuits, the interface can operate in full duplex manner, supporting concurrent data flow in both directions. The standard does not define character framing within the data stream or character encoding. The RS-232 standard defines the voltage levels that correspond to logical 1 and logical 0 levels for the data transmission and the control signal lines. Logic 1 or mark is represented by -3 volts to -12 volts level. Logic 0 or space is represented by +3 volt to +12 volt with reference to common ground pin on the connector. Consequently, the range between -3 volt and +3 volts is not a valid RS-232 level. The control signals indicate the state of nodes to each other for easy and reliable data. These signals may have differing polarity. Some signals are asserted or are in active state or called as true when they are logic 1, while some are true when they are logic 0. The voltage levels inside computer motherboard are much less in range, such as 0 to 3.3 volts or 0 to 5 volts, while RS-232 requires much higher voltage signals for same signal, such as +12 volt or -12 volt. Therefore, special driver circuit IC is required to translate logic levels in both directions. These also protect the computer's motherboard from short circuits or transients that may appear on RS-232 interface. RS-232 devices may be classified as data terminal equipment DTE, such as a computer, or data communication equipment DCE, or a modem. This defines at each device which wires will be sending and receiving each signal. The standard recommended but did not make mandatory the D subminiature 25-pin connector. According to the standard, male connectors have DTE pin functions and female connectors have DCE pin functions. Other devices may have any combination of connector gender and pin definitions. An image of 25-pin subminiature D-type connector popularly used in decade of 90s is given in figure 5. The standard specifies 20 different signal connections on this. Since most devices use only a few signals, smaller connectors can often be used. Personal computer manufacturers replaced the DB25M connector by the smaller DE9M connector shown in figure 6. Different pin numbers were used for the signals discussed in next section. This connector with varying pinouts became common for personal computers and related devices. Since the 9-pin connector is most commonly used nowadays at the rear panel of a desktop computer or PC, we will discuss only signals on this connector. The signals are grouped into two categories: data signals, which carry data in either direction, and control signals, which are used optionally to establish a handshake between sender and receiver to implement flow control. The data signals are: 1. Transmitted data, or TXD, pin number 3. This is serial output of computer to another device such as a modem. 2. Received data, or RxD, pin number 2. This is computer's serial input sent by modem. 3. Common ground, CG, pin 5. This provides return path for the signal currents. The control signals and their usage is as follows: 1. Data terminal ready, or DTR, pin number 4. This indicates that computer is powered up and enabled to send and receive. 2. Data set ready, or DSR, pin 6. This indicates that modem is powered up and enabled to send and receive. 3. Request to send, or RTS, pin 7. This handshake output signal is sent by computer to modem, indicating that it is ready to receive data from modem on RxD line. 4. Clear to send, or CTS, pin number 8. This handshake signal is enabling signal sent by modem to computer, permitting it to send the data on TXT line. 5. Ring indicator, or RI, pin 9. This is sent by modem to computer that a remote computer has dialed this modem and ring is activated by telephone exchange. 6. Data carrier detect, or DCD, pin 1. This is sent by modem to computer that dial tone is received from telephone exchange. To summarize, TXT and RxD are data signal, CTS and RTS are control signals for handshaking, while DSR and DTR show status of the computer and device, and lastly RI and DCD are telephone exchange related signals. Since last 2 decades, the telephone line modems are out of popular usage, and RS-232 is used most commonly to connect computers to computers or to other devices using fewer lines than shown above. There are several standard cables defined for connecting a PC to a device such as a modem or a printer or a mouse. Now that the modems are defunct, the same cables are used to connect PC to PC or PC to other devices. These cables are popularly called as null modem cables, since no modem is envisaged at the other end, but the software in PC works as if it is still sending data to a modem. Many types of such cables are in use, and we will discuss only 3 main types here. 1. 3-wire cable. Figure 7 shows basic 3-wire connection. TXD of the computer pin 3 is connected to RXD of the device pin 2. RXD of the computer pin 2 is connected to TXD of device pin 3, and ground pins pin 5 of both are connected together. This gives us basic serial data transmission without any handshake. 2. 5-wire cable. This uses 3 wires or connections shown in figure. In addition, it uses 2 pairs of CTS RTS as follows. CTS output of computer pin 8 is connected to RTS input of device pin 7 and vice versa. Whenever computer is ready to receive, it makes its RTS signal true, which enables CTS input of device, and device sends data. If computer is too busy to receive data, then it makes RTS signal false, which blocks further transmission by device. This way, the handshaking signals implement a flow control and ensure that no data is lost in sending because the receiver is not ready to capture it. Second pair of CTS RTS controls flow from computer to device. 3. Full 7-wire cable. This uses 7 wires or connections shown in figure 8. Notice that there are 3 pairs of signals. First pair of TXD and RXD for data transfer, second pair is for DSR and DTR for status monitoring, and third pair is for CTS and RTS for handshaking or flow control. Original standard projected a maximum length of cable between 2 nodes to be 15 meters, but by using a cable of low capacitance and good conductance, it is possible to get reliable communication up to 300 meters now. The RS-232 compatible serial interface in a desktop PC is called COM port for communications. Usually each PC is provided with 2 ports, COM1 and COM2. They can be easily detected by presence of 9-pin male connector at the rear of the panel. In modern PCs and laptops, physical COM ports have now become defunct. Instead, USB ports are more commonly provided. Thus, a USB to serial converter cable or dongle is used, which connects to one side PC side to USB port and other side is a 9-pin standard COM male connector. Inside PC, a software driver program creates a virtual COM port. The user application sends data to this virtual COM port through its driver, assuming that it physically exists. The driver software routes this data physically out of the PC through the USB port. Several virtual ports can be created in a PC. Each virtual COM port is assigned a number such as COM3 or COM4. UART is a hardware block or a circuit implemented in an integrated circuit or IC or hardware to implement COM port. It is an acronym for Universal Asynchronous Receiver Transmitter. This block carries out all desired functions of converting parallel data into serial bit stream and vice versa. All the logic mentioned in asynchronous serial communication in section 2.2 is implemented by this IC. On one side, it connects to microprocessor by a high speed bus. On the other side, it connects to remote device or modem or other PC through serial data stream. UARTs have been designed by several manufacturers for several different microprocessors. We will focus on most commonly used IC design called 16550, which was used first time in IBM PC and is still popular after last 35 years. Original UART chip or IC was developed by National Semiconductor and was called as 8250. It was later improved in design and called as 16550, which is used still today as an improved version called 16550D. Main features of the UART IC 16550D are: 1. The ability to convert data from serial to parallel and from parallel to serial using internal shift registers. 2. Using a built-in baud rate generator circuit to control transmit and receive speed or baud rate. 3. Handshake lines for control of an external modem controllable by software. These lines allow slow peripherals to match the speed of high-speed computer by pausing between successive byte transfer. 4. A facility to interrupt the host microprocessor on various events such as arrival of data, occurrence of data error or line fault. UART comprises of many registers accessible to CPU. They are used for variety of jobs such as holding the outgoing as well as incoming data, control the mode of operation, set baud rate for transmission and receiving, indicate status of serial line between two devices and any other errors in the transmission, decide various events which when occur may generate an interrupt to CPU. This chip has a built-in first in first out or FIFO 16-byte buffer for both incoming and outgoing data characters. This gives the host microprocessor or CPU more time to respond to an interrupt generated by the UART without loss of data. For example, assuming that buffer is initially empty and the arriving character rate is about 1 milliseconds at 9600 baud, it can receive and store data up to 16 milliseconds without host attending to it, without any data loss. This gives significant flexibility to host processor to attend to other high priority tasks first and then come back to UART and pick up all 16 characters in one go. The standard baud rates prevalent in old computer industry are 50, 75, 110, 150, 300, 600, 1200, 1500, 1800, 2400, 3600, 4800, 7200, 9600, 19.2 kbps, 38.4 k, 57.6 k, 115.2 k, 230.4 k, 460.8 k and 921.6 k. The UART can also be programmed to non-standard baud rates other than those specified above, but both nodes must strictly follow them for reliable communication. UART permits asynchronous operation that sender and receiver clocks may not be of the same frequency. It allows 4 to 5% difference in frequency of sending and receiving nodes. This is possible because receiver clock gets synchronized to sender's clock at the beginning of the each start bit. By design, this is an inefficient protocol because to send 8 data bits, we need to send one start bit and one stop bit. At the receiving end, start and stop bits are stripped off and only 8 bits are sent to the host computer. Thus, out of 10 bits sent, only 8 bits are used and hence efficiency is about 80% only. Hence, this protocol is mainly used for short length with peripherals which transmit data slowly and infrequently, such as a mouse, a keyboard or a modem. In case of peripherals which require high speed data transfer, synchronous serial transmission is preferred. This brings us to an end of discussion on serial interface. In the third module, we will cover the parallel interface and its application to connecting printers.